Good morning, everyone. Next algorithm is shortest path algorithm. Name itself indicates what this algorithm is all about. Given any source and destination, our task is to find the shortest path between the source and the destination. Okay, there will be a lot of possible paths for the destination. If you leave from a certain source, you should be able to reach your destination in the shortest possible path. So this algorithm is to find out the shortest path between the uh, 2 points, that is source and destination. Usually shortest path, how it will be is, here you can see 5 vertices are there, and they are connected to one another, and they have got the edge with weights. Okay, weighted edges are there. So question will be like, what will be the shortest path from A to all other vertices? Okay, I'm not interested in just finding out shortest path from A to C. Okay, the question is to find out the shortest path from one particular vertex to all other vertices. That is, I want to find out the shortest path between A, from A to all other vertices. Okay, there are 4 other vertices. From A, you need to find out the shortest path to reach all other different vertex in the graph. Okay. See, in exam, they may ask you to find out the shortest path between C to all other vertices. be careful how they ask the question, because they will be asking one particular node. From that node to every other node, you need to find out the shortest path. Usually, it will become an habit to find out the shortest path from A itself. Okay, but that will not be the case. Question may be asked in any ways. Okay, so our task is to find out the shortest path between A to rest of the vertices. A to B. See, A to B, you have a direct edge with a weight 6. Are you going to take this path A to B? But its weight is 6. So what we can do, we shall go to D, and then from D to B. If you take this path, what will be the cost? Cost will be 3. Is it clear? See, A to B, we know that direct route is there, direct edge is there, but it will cost more, 6. But if you go to D and then come to B, cost will be less. Is it clear? So we have to take the path, this path, A, D, and B. Similarly, A to E. A to E, we can take the path A to B and E, but the cost will be 8. So instead, what we can do, we can go to A to D, D to E. Then cost will be low, 2. Okay. A to D is, this is the minimal path, that is with the cost 1. So we will take A to D. A to C. Then which path to take from A to C? Okay. A to D and E. Okay. It will become 2 plus 5, 7. Okay. A, D, E, C. In that way, you can reach C, or you can reach C directly, A to B to C. But here cost is 11. Here cost is 7. So which one is minimum? This 7 is minimum. Okay, with the minimum cost, we need to reach the destination. Is it clear? Shortest path from one particular node to every other node in the given graph. See, from vertex, shortest distance from A to all other vertices. For B, it is 3. For C, it is 7. For D, it is 1. For E, it is 2. Okay, this is the path to B. This is the path to E. And this is the path to C. Is it clear? So this is the path we are going to take. Shortest path from one particular node to all other vertices. Okay. This graph was simple, only with few number of edges. So manually, like by seeing the diagram itself, we have written this. But there is an algorithm to perform this task, to find the shortest path between the vertices. There is an algorithm. See, this is also called as single source shortest path. Single source means from one source we are trying to find out the shortest distance to all other vertices. So it is also called as single source shortest path. The algorithm is Dijkstra shortest path algorithm. Okay. A very famous algorithm. You might have heard about this name at many places. So using this algorithm, we can find out the shortest path from that particular vertex to rest of the vertices. Okay, this is algorithm is called as the Dijkstra's shortest path algorithm. Okay, so we need to, in this algorithm, anyhow, we are starting with the vertex A. From this vertex, I want to travel to rest of the vertices. Okay, so this is the source vertex. I need to find out the shortest distance using Dijkstra algorithm. First, you just maintain a table where we list all the vertices, and right now it's shortest distance from A. Okay, from A we will be starting. So it's shortest distance to all other vertices. We have to write it down. And to arrays, you can say. One visited and another one is unvisited. This is the initial condition. We have not yet visited any vertices. So all are unvisited vertices. So initially what we will do is distance. See, we have not yet started tracing the graph. So from vertex A to vertex A, it will be 0. And we say that for all other vertices, it is infinity. This is the initial condition we will start with. Okay, from vertex A to A, it will be 0. No, there is no path. For all other vertices, we'll keep it as infinite. Okay, we have not yet started tracing. This is the initial condition from where we are going to start. Is it clear? A to A is 0. For rest of the vertices, we'll take it as infinite. Next. Okay, and we'll start with the unvisited vertex with the smallest distance in this table. Okay, these are infinite. So we have to start with A and its distance is 0. See, we know there is no path, but we are going to start from there and we'll see the table with the smallest distance. In this table, which has got the smallest distance is 0. Okay. And then from this vertex, we'll find out the distance of the neighbor vertex. Okay. We are in vertex A. When we are in vertex A, we'll find out the distance from this vertex to the neighbor vertex. From A to D, the distance is 1. From A to B, the distance is 6. Is it clear? From current vertex, 0 we have written because assuming that from source we have traveled to A, which is 0, 0 plus 1 and 0 plus 6. So that is the distance required to travel to D and B. See, once you find out the distance from our whatever vertex you are tracing to the neighbor vertex, then we say that we have visited A. Okay, we have visited A. That means we will write down A here. Okay, we will write down A here. See, now I got the distance for B and C. And you have to check whether C is greater than infinite or less than infinite. C is less than infinite, so we will write the C value here, 6. 6 is less than infinite. For B, we got the distance, so we'll write 6 here. D, at the distance 1, here infinite is there, we'll write 1 here. Okay, 6 is the distance to B and 1 is the distance to D, and we have visited A. Okay, A is over. We have visited vertex A. Next, again in the table, you have to check which one has got the minimum distance in this entire list of values. So A is visited. This is over. Next, among these values, D has got the least weight. Okay, minimum weight. So we will be moving to D. Okay, we will be moving to D. Is it clear? So we are in D now. When you are in D, what you must do is you have to find out the distance to its neighbors. Okay, from D to its neighbors. D neighbors are B and E. You have to compute the distance. See, from A to D we have already reached. From D you have to find out the distance to B. That is, from A point, what is the distance to B? Because from A to D we have reached. So now you have to calculate through D. If you go to B, what is the distance? For A, what is the distance? See, we are talking from A point of view. From A we have come to D. Okay, now A has to check from D. It is if it goes to B, what is the distance? Okay, so A, if it goes to B from D, distance is already to reach D we need 1. For D to B it is 2, 1 plus 2. To reach D, A has required 1. So to reach E, 1 plus 1. So distance to E is 2, distance to B is 3. Is it clear? Now this distance will compare with the table. 3. New distance to B is 3, but previous distance was 6. 3 is less than 6. So replace 3 here. And E. E distance is infinite, but 2 is less than infinite. So replace 2 here, replace 3 here. Is it clear? So 3 we got here, 2 we got here, and D task is over. So we will mark D as visited. Okay. D is visited. We have updated the table and D, it's visited already. Okay. A is over, D is over. Next, again, from the remaining 3 vertices, which one has got the minimum distance? Among these 3 values, E has got the minimum distance, that is 2. Okay, E value is 2. So now start from E. From E, you try to find out the distance to its neighbors. B and C are the neighbors of E. Okay, to reach E, we know we need value 2. So from E, if you want to reach to B, what is the distance? And from E, if you want to reach to C, what is the distance you have to calculate? Okay, from E to reach B, the distance is 2 plus 2. 2 is to reach to E, another 2 is to reach to B. Okay, 2 plus 2. From E to reach C, E distance is 2 and here distance is 5. 2 plus 5, which is equal to 7. Okay, now we got 4 and 7 new distances. Now compared to the table, 4. Distance to B it is giving 4, but our distance it is already less, which is 3. So we'll not replace this. Distance to C is 7. In our table it is infinite. 7 is less than infinite. So we'll replace 7 here in place of infinite. 3 will remain as it is. Okay. 3 will remain as it is. 7 is replaced. Now E task is over. We'll mark E as visited. Okay. E is also visited. A, D, E. These 3 nodes are visited now. Only 2 remaining unvisited nodes are there. Okay, B and C. Among B and C, which one has got the least distance now? B has got the least distance. So next we have to trace the node B. Okay, B has got the less distance in the table. We'll come to B. Now B to its neighbor, B to untraced neighbor is only C. Rest of the nodes are already visited and we know that it has got shortest distances. Only remaining node is C. To reach B, we required cost 3. To reach C from B, that is nothing but 3 plus 5, which is 8. Okay. From B to C, it requires 8 cost. But C value already it is less than 8, 7. So we are not going to replace this new value to C. We will keep it 7 itself. So there is no need to update. Now we will mark B as visited. Okay, we'll mark B as visited. Next, only remaining node is C, and there are no neighbors to it. So finally, we'll come there. We'll check the final condition, and we'll mark it as visited. C has visited. Is it clear? See, here we will maintain a table based on that table value. In the table, we'll first initialize the table to infinite values, and with the neighbors, whichever is having the shortest distance, we'll start tracing from there. From that neighbor, we'll calculate the distance to its neighbors, and we'll go on updating the table. Okay, this table is updated, and based on this table values, so finally we'll come to know the shortest distance from A to all other vertices. So shortest distance from A to B is 3, A to C is 7, A to D is 1, A to E is 2. So this table gives us the shortest distance from A to rest of the vertices in the. Okay. So algorithm is as follows. Let distance of start vertex that is initialized to 0. Rest of the vertices is initialized to infinity. See this is just for your understanding. Okay, algorithm. While vertices remain, you have to give one condition. Okay, until this condition becomes true. Until this condition fails, we will be executing these intermediate steps. Visit unvisited vertex with smallest known distance from the start vertex. Okay, in our case, this was the first line. We have visited D for each unvisited neighbor of the current vertex. That is, we have visited here for each unvisited neighbor of this current vertex. Okay, for each unvisited neighbors means B and D for this vertex. Calculate the distance from start. Calculate the distance from start means this is the starting point. To reach D it was 1. To reach B it is 1 plus 2. Again, to reach D it was 1. To reach E it is 1 plus 1. Calculate the distance. If the calculated distance of the vertex is less than the known distance. Okay, to reach B we got 1 plus 2. Earlier in the table it was infinite. If the known distance is, if the calculated distance is less than known distance, you replace this calculated distance in the table. Update the shortest distance of this vertex. And one more thing we can do, update the previous vertex with the current vertex. That is, we can also keep track of to reach B, we have to go through D. Okay, that also we can store it in the table. Okay, here one more column you can put. That is for B, distance is 3 via D. You can also store that information. Okay, to reach E, distance is 2, but you can reach it via D. Okay, that information also you can store. Update the previous vertex with the current vertex. Okay, this is that information. So you'll be doing that. Visit the next visit unvisited neighbor. Okay, next we are going to go for E with the minimum distance. Add the current vertex to the list of visited vertices. Okay. Once you have calculated its neighbor distance, then only you add this to visited vertices. Okay, immediately we'll not add. Once we calculate the distance to its neighbors, then only we'll add this to the visited list of vertices. Okay, so this is Dijkstra algorithm. This algorithm is used to find out the shortest path from one vertex to the different vertices. And for this also there is a lab program. There I will be tracing it again with example line by line. There will be a question on this in the exam. So in exam, they will give you a graph and they will ask you to find out the shortest path between A and all other vertices. They may ask you to use Dijkstra algorithm, or simply they may ask you to find out the shortest distance. Okay, in both the cases, you have to use the same logic. Is it clear? Okay, there is a animated video here. Whatever I have explained, same thing is present here. Just watch this. All of you mark the attendance. Quickly mark the attendance. Okay, so watch this video. Same thing is explained in an animated way. Okay.
To understand what Dijkstra's algorithm is and how it works, let's start with a scenario. Let's imagine that we have a variety of different towns scattered in different locations. Some of those towns are connected to other towns with roads, such that we could travel along a road to go from one town to another. Not all roads have the same travel time, though. One road might take 3 minutes to travel through, while another might take 4. And our question is this: what's the fastest way to get from town A to town B? This is a specific example of a more general problem in graph theory, where we have vertices, in this case our towns, that are connected by edges, in this case our roads. Together, the vertices and edges form a graph. And in particular, this graph is a weighted graph, because each edge has some value, or weight, to indicate how costly it is to travel along that edge, measured in either distance or time. And with this graph, we'd like to determine the shortest path from one vertex to another. So how does Dijkstra's algorithm allow us to do this? Ultimately, we need to figure out how many minutes it will take to get to town B. In doing so, though, it might be useful to figure out how many minutes it would take to get to the other towns too. So ideally, we'd want to label each town with a number, representing the shortest time required to get there. But of course, we don't know that information yet. So instead, we'll label each town with the shortest time we've found so far to get to that town. Before we've started the algorithm, we don't have any known way of getting to the towns, so we'll label them all with infinity. The only town that we can label correctly is our source, town A, which we can easily label. We're starting there, so it takes 0 minutes to get to this town. Once we've found the shortest path to a town, let's call that town Explored. For all other towns, we'll consider them Unexplored. We don't yet know what the shortest path to them is. So what can we do next? Dijkstra's algorithm repeats a two-step process. First, we update our estimates, and second, we choose the next vertex to explore. So let's start with the first step, updating our estimates. We know we can get to town A in 0 minutes, and because we can get from town A to town C in 3 minutes, we know we can get to town C in 3 minutes. That's much better than our current estimate of infinity, so we'll update our estimate to be 3. And we can do something similar for town F. We can get there in 2 minutes, so we'll update our estimate. After we've considered all possible roads connected to town A, we're done with this step. And now the next step is choosing which town to explore next. And the rule is quite simple. The town we explore will always be the unexplored town with the smallest estimate. In other words, the next town we explore should be, among all of the unexplored towns, the one we know we can get to the quickest. In this case, that's town F, which we can get to in 2 minutes. And now, the two-part process of Dijkstra's algorithm repeats. We first update our estimates by looking at the towns connected to town F. It takes 5 minutes to get from town F to town G. So if we can get to town F in 2 minutes, then we can get to town G in 7 minutes, the sum of those two values. Likewise, we can get to town B in 8 minutes, and we can get to town E in 5 minutes. We can also get to town C in 4 minutes, 2 minutes to go from A to F, and then another 2 to go from F to C. But 4 minutes is actually more than our current best estimate for town C, which is 3 minutes. So we don't want to update anything here. Remember, for each town, we want to store our best estimate for the shortest amount of time required to get there. So let's keep going. The second part of Dijkstra's algorithm tells us to explore the unexplored town with the smallest value. And in this case, that's town C, which we can get to in just 3 minutes. And the process repeats again. Going through town C, we can get to town D in 7 minutes, and we can also get to town E in 4 minutes. 3 minutes to town C, plus 1 minute from C to E. That 4-minute estimate is better than our current estimate of 5 minutes, so we'll update our estimate for town E from 5 to 4. The next town to explore is town E. Among all the unexplored towns, it has the smallest value. Notice that each time we explore a new town, it's guaranteed that we will have found the shortest path to get to that town. Since if there were some shorter path, we would have explored that shorter path first because we prioritize exploring these smaller values. And through town E, we can get to town B in just 6 minutes. 4 minutes to town E, plus 2 minutes to go from E to B. So we update our estimate for town B to be 6, which is better than the previous estimate of 8. And now, the next town to visit is town B, our destination. And that tells us that the shortest time needed to get from town A to town B is therefore 6 minutes. And that's Dijkstra's algorithm for finding the shortest path in a graph. Now, there are a few things worth pointing out here. The first is that technically, our algorithm has only given us how long it will take to get from town A to town B, and hasn't actually given us which path to follow. In order to actually reconstruct that path, we'll need to add a step to our algorithm. Every time we update our estimate for a town, we should also keep track of what previous town we visited in order to get to this new estimate. If we keep track of that for each of the towns as we progress through the algorithm, then at the end, we can figure out what the best path is just by following those arrows backwards to the beginning. Also, it's worth noting that this algorithm only works correctly if the weights of all of the edges are non-negative, since otherwise some negative length path might result in a shortest path that our algorithm wouldn't be able to find. Another thing worth thinking about is how we efficiently determine which unexplored town to visit next. We want to always pick the unexplored town with the current smallest estimate, so some kind of priority queue that gives us efficient access to the next town to visit can make our algorithm faster. And that's Dijkstra's algorithm for finding the shortest path in a graph. We keep track of a distance and a previous town for each vertex. The distance for all vertices starts at infinity, except for the source, which starts at 0. And then, as long as we haven't explored the destination yet, we pick the unexplored vertex with the smallest distance to explore next. We consider all edges connected to that vertex, and if we can come up with a shorter path to a neighboring vertex, then we'll update our distance estimate and remember which town we came from. Once we've explored the destination, we have our answer. We'll know how quickly we can get to the destination, as well as what the shortest path actually is. The shortest path.
Okay, that is Dijkstra's algorithm. Remaining, we shall continue in the next class. Thank you.